Welcome to the Bytecode, where we look at smart contracts with the people who wrote them. I'm your host, Shafu, and today's guest is John. John, thanks for taking the time, man.
Hi, Shafu. Thanks for inviting.
Yeah, for sure. So, John, why don't you briefly introduce yourself and introduce what you're going to present today, and then you can share your screen and we jump directly into it.
Yeah, sure. So hi. My name is Jean. As you can imagine from my first name, I'm from France, and I'm basically a smart contract engineer at Luxo. And I work on the Solidity implementation of LSPs, which are the Luxo standard proposals. So it's basically smart contract standards around smart contract based account and tokens and NFT, and I write the implementation in Solidity with the rest of the smart contract team. And yeah, and I've been into Web3 and smart contract for um, since mid 2019. I've learned through workshops in central London, and then got involved uh, more. And now I've been at Lukso for over a year and a half now. And today what I'm going to present, it's Lukso standard proposal number 6, LSP6, which is the key manager, and it's basically a smart contract that use a set of permissions and access control to basically to control another smart contract account and allow basically multiple entities and controllers to control this account through different permission type of permissions. So yeah, that's what I will be going through today. And yeah,
Awesome.
that's pretty much it.
Yeah, share your screen and how John and I, this is the first time that we talk. I just saw John on Twitter and I thought it would be super interesting to have you on. So yeah, exciting to look at the slides first and then at the code.
Yeah, so there's quite a bit of content, but I thought before diving into the Solidity code, that I could uh, show some slides and some diapo from previous presentations. So we did some hackathons in the past, and we did some we have created a lot of content. So yeah, I think the idea is really um, to give an overview. We have a lot of slides. You can see it's 235, but I'm just going to do 235 slides. I'm going to do just the LSP6 section. I just want to double check if is it visible my screen. Can you see the slide?
Looks good.
Yeah. Okay. Super. Okay. As I say, I'm going to present the key manager, and before to really get straight into the Solidity code, I think it's important to understand the reason why at Lukso we created this standard, and the reason why the contract really exists and what's the purpose of it. And it's mainly around contract ownership and management. So at Lukso we have a set of contracts, including one called a universal profile, which is a smart contract based account. And the idea is really the standard idea, in the smart contract design pattern. We have a ownable pattern, a basic, basic design pattern where you have a contract that is owned, that has an owner, and it has some functions that are restricted only to the owner. And the idea of that is that it's great because you are control and of specific functionalities. But there is a bit of problem when it comes to really, if you think of a contract as, something that interacts a lot on the blockchain, that perform a lot of interaction, especially if it's a smart contract based account. So the idea is that if you imagine this is a smart contract based account, and this is the owner, Bob, basically, because Bob is the owner, he has to do everything on his own. And if it has to really um, any restricted function, like function for interacting with the outside world, which are restricted to him, everything has to be done by itself. Um, if the contract connects to the app and has to set some data related to the app, uh, the app has no way to set these data themselves. So Bob has to do everything. He has to set all the data itself. It's quite it's quite a lot of workload if you think about it. And there's also all the ideas around mistake and security. If if basically Bob loses his private key, or if it lose access to its account, really, there's no way with a normal pattern to recover that. You have a contract is set stone on deployment. I mean, it's set in stone. You can always upgrade the ownership, but if at the time the owner is Bob and Bob loses private key, uh, there's no way the contract really is basically uncontrollable and usable anymore. So yeah, that's really the big problem, is that you have to do everything yourself with a ownable pattern. So there is something online that if you do some research around ownable, that's called an overpowered owner, meaning that Bob has too much power. And what we should think about instead is to segregate what I call segregating duties, meaning we can give some privileges to other addresses, so that we can also, dispatch the workload of what can be done on the contract. But we can do that while still keeping control of the account. So we still have admin access, uh, but we can still allow other entities to interact with it. And you can think about it a bit the accounting department in a company. There is the main accountant who can do everything in the accounting software, and there are the other accountants that can access some part of the software, like the purchasing side of the invoicing side, or also have more privilege. They can add and remove new new users in the software. So it's a bit the same. The idea is really we keep control, but we can segregate and dispatch the workload. So what happened with LSP6 is that really LSP6, it's really this idea of segregating the duties. So you have the main account, the main smart contract, and you have the key manager, which is another separated account. And you have multiple entities that can interact with the account via this contract, which is the owner. And all these entities have permissions set here on the smart contract based account. So really this is the motivation. So the reason why we have the key manager is because we have limited use also. Because since only the owner can interact with it, has to do everything, and you can have a bit of limited usability when it comes to interacting with the app. And with a key manager, you allow to have more interaction flow with a contract. You can have other basically address that can interact with a contract based on the permission that you allow them to do. So really, I think it's a good sentence to summarize is the key manager allows to control who can do what on the universal profile, which is basically the linked account in this case.
Yeah, John, can I ask a question?
Yeah.
So maybe to summarize it, please correct me if it's wrong. It's similar to a multi-sig, but there's like a super admin who can set for other addresses specific can grant them the specific functions that they can call.
Yeah.
Specific permissions.
So it's a mixture of a multi-sig and a rule-based access control. If you think like this. So like multi-sig, it's you to perform a transaction, it has to be validated by a threshold of signer. It has to be signed. It has to be validated by all the signer in the multi-sig. And role-based access control, it's more to give control on who can do which action. So like in OpenZeppelin, it's often the role of a minter, the role of a poser. The only difference with role-based access control is that with role-based access control, it's a module that is plugged in within the contract that needs this functionality. While with a key manager, the contract is separate. The contract who verify the logic is separate. Does that answer the question?
Yeah, yeah, okay. That makes sense.
Yeah. Okay. So yeah, and so that's how the key manager works. It allows really to grant or restrict, depending on which perspective you look at it, to who can do what on the profile. And you can think of the addresses apps, devices, or third parties, or any other kind of accounts, really. And it does that with a permission system, which is defined in the standard. And so that third party can perform this specific action on behalf of a universal profile. So you're basically saying, basically Alice can have a permission to set data on my account, and Alice set data on my account on behalf of my account. And Bob, let's say Bob can be the main admin. So in the past, like in the past, we saw Bobby was the owner, the sole owner. He's the same. He's the sole owner. It's just the difference is it has all the permission. It has pseudo right. And and then you can have as many users as you want with permissions. So you can add, remove these control, what we call these controllers. So I call that these addresses controllers. And and basically how it works is Alice make an interaction through the key manager to interact with the UP, and the key manager reads the permissions of the user of the address. If that can be anything, that can be an externally on the account, a smart contract. It's gonna read the permission of this address stored on the account, see what what is it trying to do, and based on what it is trying to do compared to the permission that it has, it will allow or it will not allow. So here it has set data, and this set data is going to allow for call and let it go through on the account. And if another user tries to do an action that it doesn't have a permission for, it will not authorize. So here Carol tried to do set data, but it has only the permission call and transfer value, so it just not allow. And so you can think of it like that. It can restrict, you can do what, you can authorize, and you can allow interaction from multiple sources. So I think it's really based on how you interpret the permission system. And the key manager had in its current design in the 3D code, we will see it has basically three main paths that have separated on colors. So the green path is set data, the other purple path is execute. So set data is for setting some metadata into the contract storage here. So this is what is in yellow. Execute is the functionality in the smart contract based account for basically interacting with the rest of the network. So like doing basic operation from transferring a native token to interacting with other contracts. And transfer ownership is the management and admin part is for basically changing the owner. So you can have at some point a key manager as the owner, and you can decide, okay, I don't want to have a key manager anymore. I want to become again the sole owner, my externally owned account. And you will do that through a two-step process: transfer ownership and accept ownership. And that's pretty much the main idea. And so in a nutshell, there is we have added more permission to it, but like in a nutshell, that's the three categories of permission that I mentioned in the previous slide. So we have a change owner, which is for contract ownership, change permission and add permission as well. Set data, it's about setting the metadata in the contract storage. and anything, and then the rest is around contract interaction. So our Lukso LSP0 contract has different type of operation to when it does external call. So it can do a regular standard call, static call, as we all know it, just read-only call, delegate call, uh, and deploy and transfer value just for doing native token transfer. And sign is more something to be used for logging purposes. If you log into a DApp, if an address tries to use your account to log onto a DApp, it will check this permission before logging in. So yeah, I think probably it's best to jump straight to the code because then it's more fine grained. But I can jump into the other. I have other slides and docs page ready in case. Or I mean, or do you want to look at anything else? And do you have any question? Should I flow on those or?
Yeah, this is really exciting, dude. So basically, what you guys have built is, I think you could compare it to a permission system as you can find it on GCP or AWS, but it's basically for
Mhm.
smart contracts,
It's pretty
wh-
much that, yeah.
which
Yeah, yeah.
is great. What I'm asking myself right now is, this seems like a very needed thing. What
Mhm.
are people doing right now to solve something like that?
So at the moment, it's mainly, I would say, um, role-based access control or yeah, multi-sig. Um, or when it comes to smart contract accounts, it's more, um, yeah, it's more, I would say, really role-based access control. But the problem is with this is really you have, um, like you have access control embedded with your contract by default when you
Hmm.
deploy it. While here, what you have, the idea is that you have a contract separated from the actual permissions. So the permission line to your contract, but the contract key manager is the one for verifying. Um, so I mean, from what I saw, like really the other, yeah, I mean the other module that are used from what I've researched is things around governance. So like you have like the Governor Alpha, the Governor Bravo, all these type of contracts that exist to really to manage governance. And the idea is that with a key manager, really the key is that we try to standardize also the permissions that so that they are uh, flexible and like they are generic and modular enough to enable different use case.
Hmm.
So like set data, it's a generic permission, but you need to also, I didn't go through it yet, you need to also mention which data keys, which entries into the storage you can control. So you could use set data for specific subset of entries into your storage. So you can basically say, let's say if the contract that the key manager controls is is a contract that has data in it related to governance, you can say, I'm gonna give Alice the permission set data, but I'm gonna allow Alice only to modify the entries related, the data related to the governance proposals. So you basically fine grain control what like what a controller can edit, and you can achieve the same goal this way. Or you can also do the same way for the interaction. You can say, I will allow, like I will allow the Uniswap pool, let's say contract, to just use my account to interact with a specific other pool. So you just say which address you can interact with or which data you can edit. So I think this is also where the key manager comes very handy. It's because there is these permissions, but there is also the fine-grained control of which data and which contract or address you can interact with. And that allows you to basically build different type of like of access control mechanism.
And this is super cool. You basically abstracted away the permission system that normally you would directly define in the smart contract itself.
Exactly. And what's also interesting is you can have basically you can you can have you can evolve the permission system of your main account over time. Really, the key manager really it's just there to the whole purpose of a contract is really to verify the permission. It has like a module for meta transaction. I can show it as well, but the main core of a contract is purely for verifying permission.
Mm.
And the key is that because the permissions lie here in the actual account, what you can do is that you can say, okay, at the moment I use key manager version 1. And at some point, you can say, okay, there is a new key manager, which much more feature that has been released, and you can do the path that I was showing earlier. I think you can do like the transfer ownership and accept ownership path. Full screen. You can do transfer ownership and accept ownership, and you can upgrade to key manager version 2. But after you have upgraded, you don't need to migrate all the permission again because the permission lives here. They live in the storage of the actual account. They
Mm.
don't live into the key manager. So that's also like an interesting aspect of it, I would say.
Really cool stuff. Should we jump into the code?
Yeah, let's get into it. Yeah.
Awesome.
So I think we're gonna do it with the interface maybe first. So basically, the idea is when we write the standards, so we have like all the so like the I mean really in a nutshell, the project is it's a hard hat project with we have a set of foundry tests, and for each standard and contract, including the key manager, we first write the interface with all the functions defined into the standard. Um, and basically, the interface includes the event and the function that the contract implements. So it's fairly, I mean, I would say it's fairly straightforward. The, the only function that the contract has are the target function. So this is the address of the contract it's linked to. So in the previous figure, it's basically this contract. So if you query this function, you will get the address of this contract. The get nonce, it's because the key manager has it allows to do meta transactions. So you can submit transactions that you're not executing yourself, that someone else has signed, and you just pay the gas for someone else. And we need some way to we manage that through nonces. And then we have these basically four functions. So we have execute, which is when you want to perform the interaction yourself on the account. And execute batch, it's the same as execute, but you execute multiple transactions. And the same fashion with execute relay call. So execute relay call is the meta transaction. So to give an example, let's say I want to set data in my account. I will call the execute function on the key manager. Uh, it will see my address, it will read the permission, it will verify them, then it will forward them. I will pay for the gas. With execute relay call, basically, let's say you have set data access on my account. You sign a transaction, you send a payload with a specific format. You give it to me. I submit the transaction. I pay for the gas, but it verifies the permissions from your address. So this is the difference between really execute and execute a relay call, and batch is just the batching. It's just the batch version of both of them. Yeah. So yeah, and yeah, I think the best way to go through it is to look at the core contract. So the key manager core is really the contract that has all the of the core logic. So it has the non-store for the execute relay call. It has a boolean to check for reentrancy. It has the address of the target contract that it's linked to. Um, as you can see, it's basically just um, the getter and the state variable are separated. It implements a support interface, and it inherits multiple modules. So it inherits the three modules that we mentioned, that I just mentioned in this slide. So it inherits for setting data, executing, and ownership management. And I think then we can look. So I actually have two proposals. We can either look at I think with the key manager, the probably most interesting part there are two. It's the meta transaction, how you recover a signature, you verify it, or there is really the core logic on how you verify a permission. So you tell me if you have a preference. Um,
Let's do meta transactions first.
mhm.
Um, but one question I have on the top, why did you guys need to implement the reentrancy stuff yourself and not just inherit from the Open Zeppelin
Yeah,
thing?
that's a good question. So because basically, so like these are a bit um, old slide actually. In the docs, it's more up to date on the permissioning system because we have a bit more permission that have been added to it. And we have one of them, which is reentrancy. So like it's basically to allow, we have a permission for allowing addresses to, like protocols to perform multiple interaction in the loop. So like, let's say if you want to interact with a DeFi protocol and you want to do some automated form of trading, you could want to reinteract with a contract. So it's basically because we implement that as its own permission. So when there is a reentrant call, the address making the reentrant call needs basically to have this specific permission to be able
Mm.
to interact. So yeah, that's the reason why we have that as our own as our own implementation, and not as the one from OpenZeppelin. So
Okay.
the idea is really it's really the same thing. So it really I can show a bit further down. It does so like we have like an internal function on reentrant before that checks for the reentrant status, and if the caller has this permission if a call is reentrant, basically the caller needs this particular permission.
Hmm.
So we have implemented that as a permission, but this is the kind of the advanced use case for this scenario. Yeah.
Okay.
So yeah, and does that answer the question?
Yeah, that makes total sense.
Okay. Yeah, I guess we can go into execute relay call then.
Yeah.
So yeah, I mean, so I like to approach the discussion of a function a bit like, like if you do rubber duck debugging, where you have to explain uh, like really the function like rubber duck. I mean, except in this case, I'm doing it to you. So like the idea is that basically, so I like to say like to do like when I debug the code, what I tend to like to do is to start to debug my own code. I like to say to do to perform an execute relay call, you have to and then go through the step. So basically, the idea is that to perform an execute relay call, you have to provide different information. The first one is the signature. So you have to provide the data that you have signed for a transaction. You have to provide the nonce, basically to validate that this is not a transaction that has been repeated. Validity timestamp. This is like a feature that allows to execute a transaction within specific time frame. So you can specify a transaction to be valid from a certain point in time or until a certain point in time, or both, or none of them. It can be valid indefinitely. And then you provide the message value. So it's passed as a parameter in the execute relay call function. This is just a message value. In the case of the batch transaction, the message value sent to the function has to be the total of all the values sent into the array. So there should not be any money left in the key manager. So this is how we check it. If so we basically increment as we go and compare with the total message value. And if that's the case, meaning if if all the total values sent exceed the message value, basically we haven't sent enough. And if it's the other way around, if all the total value sent is less, basically we have sent too much. There will be some money left in the contract, and we don't want that. So that's for the batch. It works differently. There shouldn't be
Yeah,
no money left on the contract.
interesting. From a gas perspective, wouldn't it make more sense to check before you execute, so you sum up all the message.values and make sure that it's equal to what you put in? Be
Um, that
I'm
that
actually not
could,
sure.
but you,
Yeah.
yeah, that's a good point actually. That's worth trying. I mean, if you think from it depends on the size also, I would say, of the array. So if you look through, if you have a very big list, you could. I haven't tried that actually, in pure honesty. So yeah, could be worth trying. But
Yeah,
yeah,
because if the assumption is, so let's say the assumption is the all transactions go through, then it actually doesn't make a difference. But if the assumption is that most likely something will fail, then it would be something would fail because there is not enough funds. Then it would make sense to check it beforehand. But just gas
so
stuff. So yeah.
yeah, yeah. So you mean if so the gas usage if a transaction will revert?
Yeah, so in this case, in this current implementation, if the last transaction fails, right, then you wasted a lot of gas. But
Yeah, that's true. Yeah, and yeah, this is actually hard. I find personally to like to make the decision
mm,
um, when if a transaction reverts. Uh, there are some cases where it might have to revert because there was something invalid or malicious that was trying to be done. So like the gas has to be the gas spent is kind of
a
like
penalty.
the penalty. But you
Mm,
have other cases where it can be the mistake from on the user side, and then in this case, you don't want the user to uh, too slashed into the gas usage.
mm.
And yeah, in this case, that's where it makes more sense here to revert to fail as early as possible. So you have to loop first. So yeah, that's I mean, I would quite like to try that and see the difference. But yeah, that's an interesting point I haven't thought about in this case. Yeah. And yeah, so yeah, that was basically the difference for the batch, for the message value for batch versus the standard one.
Okay.
So I was, yeah, so you can see there's a lot of code in the key manager. Um, and yeah, so the first thing that we do, so to perform the execute relay call, so we have to provide all these parameters, and the final one is the payload. So the payload is basically the ABI encoded function call of a function to be executed. So that's what uh, we documented in the interface in the NetSpec. So if you want to do set data, you ABI encode the set data function. So yeah, so the first thing that we need to validate is that the payload is at least 4 bytes, so that at least a function selector. And then the next thing that we do is actually the interesting part of the standard for the execute relay transaction. We need to construct an encoded message and validate that it came from the right signer. And we do that through basically standardize that into the standard. So so I think in the docs it's explained. So yeah, so to sign relay transaction, we basically take the payload, we take several things like the chain ID, we take all of that, and we construct the message accordingly. So the first thing we need is the LSP6 version is just a constant, the chain ID, the nonce, the validity timestamp, the message value that was sent, and the ABI encoded payload. We encode all of that, we concatenate technically all of that. And what we do is we use EIP 191 version 0 to basically to create the hash of the encoded message with the key manager address, the address of this key manager contract, as the intended validator. So this is how it's exactly how it's defined in EIP 191. We have a 19 prefix, we have 0 for the version, then we have a validator address, which is the key manager, and then we have all of these information. So we take all of that, we gather all of these information, then we hash them, and after that, basically we try to recover the address of the signer in comparison to the signature. So
Question.
yeah.
I've never looked into EIP 191. What's super interesting to me is I didn't know there were different versions for an EIP. That's a possibility at all. That's the first time I've seen that actually. So why are there several versions of EIP 191?
Yeah, it's actually a very thing that I also learned that is very new, that I never knew before. And you can see in the standard that there is different version. There is version 0, version 1, and version 45. And it's really it's quite interesting because if you so actually Yaman from the smart contract team at Lukso made the PR to describe that better. So the version 0 is the one that we use. It's the data with intended validator. So it's the one that you can see here. It's version 0. It's OX19 with version 0 in the validator address. Then version 1, it's based on, it's for 712. It's type structured data. I don't know in depth this one. And then we have version 45, which is a personal side message, so Ethereum side message. And the reason it's version 45 is because the letter E, the hexadecimal Unicode of the capital E, uppercase E, it's 45. So it's basically why it's version 45, because it's E. and then theorem sign message. So yeah, that's actually also something that I've never heard of, and I just discovered that at Lukso.
Interesting.
Yeah. So yeah, so we recover the so to go back to that, we recover the address of the signer uh, by basically uh, um, doing we use the ECDSA library, so we use the I tend to prefer this syntax, so it's not immediately obvious which library that you use, but in general, when you use like some of these libraries are quite common. So um, yeah, in this case, like we had implemented that in the new version of OpenZeppelin, it's implemented this function, but we in the old version it was not. So we have just a specific small library for that. It's here. Yeah, so you can see here. So what it does OX19, the prefix for 191 version 0, the validator address. So I think put it side by side is a bit easier to read. Yeah, here. So the validator address is basically passed as the first parameter. So I tend to use the USIM4 syntax for libraries and pass it like that. But you could do it with, you could do it with EIP or 191 signer, and then you pass the, and then you pass the first parameter here. So you basically have two ways to do it. You could do it this way or that way. I don't know why it's complaining here. But yeah, see it's compiling. So like I tend to prefer this syntax. So yeah, you do the validator address, the data to sign, which is basically the encoded message from here. So yeah, I think that's really the really particularity for the meta transaction on the LSP6 on the standard. And yeah, we compare the hash message with the signature. We obtain the signature, the address of the signer. Then we do a reentrancy check for set data. So set data basically is a function of the linked account that doesn't perform any external call. So we need to check if it's one of these selector. If that's the case, basically we don't toggle the reentrancy status, and then we validate the nonce. And yeah, this is actually the part that I quite like. So if a nonce is valid, we just revert. And so yeah, maybe I can show that on the nonce validation. So what we use for the nonce mechanism is we call that a multi-channel nonce. So the idea is that you have as a user, you can sign transaction through multiple channels. So a channel is basically you can think of you can think like like a service that has an API that take like a relayer. Instead of having necessarily to have all the transaction queued one after the other, you could run them in parallel and dispatch them in parallel. And yeah, so and for that we have, like on the non-store, we have the nested mapping here. So we have the address of the basically the signer. This is the first mapping for the channel ID, and this is the non-store in the specific channel. And yeah, so here's it's a bit like complex to explain. And I mean, I quite like this part because it's really around byte manipulation. So the idea is that the nonce that we provide, it's called an IDX, and it's basically a data. I don't know if you can see here. Yeah, it's like an integer that is formed of two parts. The left side is the channel ID, and the right side is the nonce. So I have actually something on Miro to explain that. So basically, when you do get, I think actually let's look at get nonce. It's more interesting. So when you read the nonce for a signer, you provide the channel, and you will get the nonce back in this channel. So just the nested mapping, and what you get return is actually not the nonce in the channel. It's like an IDX. It's like what we call an IDX. It's a value that contain both the nonce and the channel. And the reason for that is it's easier on the front end side and on the app side to handle that, because otherwise the app will have to know for every user the channel where he wants to basically when he wants to run the transaction. So we get the channel ID, which is basically a uint 128. We flip it on the left side, and then on the right side we put the nonce that we recovered. And so we end up with something that looks like this. So let's say if you want to execute a transaction on on channel 5, you read the nonce at channel 1, and you're going to pack on the left side the nonce, the channel ID, sorry, and on the right side the nonce. So yeah, it's the concatenation of these two elements here. Does that make sense? It's a bit, in general, it's a bit complex, this path of multi-channel nonce. So yeah, don't know if I explain clearly.
Yeah, explaining bit manipulation stuff is always a bit complex, but the presentation thing you pulled up is really helpful, I think.
Yeah, you mean
Yeah,
this,
yeah. This great visualization.
yeah. Yeah, so like basically what I mean, if we really look at the like if we look at the Solidity code, like what happened, I mean, I kind of enjoy like try to represent that like visually. Like what happened is the nonce. So like if you look at the code, like you have a channel ID, it's a uint 128. So it's basically just like a 16 byte long value. We cast it to a uint 256, and then when we shift on the left 128 bits. So when you do shifting, you always have to you have to provide the value in bits. So you shift 16 bytes on the left. So there is 8 bits in a byte. So 8 times 16 is 128. So you shift by 16 bytes, 128 bits on the left. So what happened is you're gonna shift it like that, and at the beginning, you're going to have just 0 here. You're going to have just plain 0 in here. And what happens is when you do OR, a bitwise OR, it's going to toggle all the bits that are 1. So it's going to toggle all the bits that are 1. It's for setting the bits basically. So it's going to set all the bits on this side. So it's going to set the nonce on this side. So yeah, that's how it works for the bitwise. So you shift and then you toggle on the right side. That's how you concatenate to the two parts. And yeah, so you do that, and yeah, this is all. Yeah, so yeah, we are really into the bits and bytes here. And when you validate the nonce, you basically have to do it the other way around. So what you do is you create a mask. So he is basically a bitwise not for a 0. So what's gonna happen? So this is the equivalent of doing this, or it's basically FFFFF. It's just 16 FF bytes. So it's basically 128 times on the right side.
Yeah.
And it's going to create just this mask. And to compare that the nonce is valid, you basically do that. So on the non-store, so like you can see on this side, it's the other way around from what we did. So what we do here is we get the we get back the channel ID by shifting on the right side 128 bits. So we do it the other way around here. We do 128 bits of shift on the right. So it's going to do like this. Yeah, very 21st century animation. And you basically going to end up with this value as a UID 8. So you discarded that. So here you have a channel ID. And then you provide that as the parameter to the mapping. And what you get back is basically the nonce in the channel. And to compare that the nonce in the channel is valid, you take the full IDX and you do an AND with the mask. So the mask is going to be, it's going to be technically like that. So it's going to be filled with 0, 1, 2, 3, 4, 5, 6. 6, 12, 13, 14, 16. It's going to be filled with 0, and you're going to basically, the mask is going to give you this value like that. You're going to compare only the side that's in on the side where there are the FFFFF. And so when you do a bitwise AND, I think I have a little thing on Miro here.
Oh, wow.
Yeah, there are a lot, yeah. Yeah. You just saw the tip of the iceberg.
Yeah.
Yeah. So like, yeah, how ending work is, and when you end 2 bits, basically it will return 1 if both bits are set, and it will return 0 if only one of the bits is set. So basically, when you mask it on the right side, basically it's going to compare the binary representation of 1, which technically is going to be 1, 0, 0, 0. I mean, we could even, without going into this is going to be like 1, 0, 0, 0, and then filled with 0. And this is going to be like FFF, it's going to be 1, 1, 1, 1, 1, 1, 1, 1. And so it's going to say, are both bits 0? Yes, it's going to then give yourself back 1. Then it's going to say, are both bits 1? It's going to say, no, no, it's 0. And same, are both bits said no, 0. And same again, are both bits said 0. And then it's going to say that. So when it's valid, basically, if you end the mask with the nonce, if it's valid, it should return you the exact nonce value. So if it returns you the exact nonce value, and this match with the right side, what you get from the storage, then that means the nonce is valid.
Okay.
Yeah. I don't know if that makes sense. It's a bit, the bits and bytes is always tricky. I kind of like working with bats and bitwise operation, but it's true that it gets often complicated to describe and reason with it.
Yeah, you have to go through it yourself, otherwise it's just a little bit too abstract. But I think you did a great job of explaining it.
Yeah. So I mean, you validate the nonce here, and once it's validated, so I'm not gonna go through it again. The bitwise AND on the right side. So you get back again the channel ID by shifting, and you increment the nonce in the channel. And then so like here the nonce validation passed, and then we check for the validity timestamp. So if the validity time, so technically, if the validity timestamp you provided to a function is 0, that means the transaction is valid for an unlimited period of time. There is no starting time, there is no deadline. So if it's not the case, then we need to extract the starting time and the ending timestamp. So this is the same. The starting timestamp, it's the left side of the uint. It's two uint 1 to 8 concatenated. So we do the same. We just shift. So we just shift on the right, basically. And the ending timestamp, it's the same. It's on the right. Yeah, so this is something that I really like to use. I like explicit conversion with uint smaller, because when you have a big uint, like a uint 1 to 6 here, you can see from um, the, the type here. When you cast to a smaller uint, it takes the low order bits on the right side, because with uint it's always on the right side. So it will discard what on the left of the unsigned integer. So yeah, so that's how we just we could like do it differently. We could shift on the other side and then cast to a byte 16 and then uint 1 to 8. But I just think it's just shorter and easier like that. And then we validate that the transaction is into a valid timestamp. So basically, if the current block is less, this current timestamp, pardon, is less than the sorry so if the current timestamp in the block is less than the time at which we specified that the transaction is valid from. If it's less than that it's you cannot run the transaction yet. So we revert with a relay call before start time. And if the current timestamp is after of the current block is after the deadline, then it expired. That's basically how that works for validating. That's basically all the validation that we do for the meta transaction or a relay call. It's all of that. And then we can go into part 2, what I was mentioning before, into the actual permission verification. Unless you have other question you want to go through.
Yeah, we're just at nearly exactly 1 hour. I don't know how much time left do you have.
Well, I can give a quick overview on really basically the overall path, and without going into very much detail if you
Okay.
want.
Yeah, sure. Let's do a quick overview.
Okay, so basically, if we to go off to go through the main path, so how permission verification works. So to verify the permission, we basically need to three samples of information actually. We need the address that is making the request. So if it's if its execute is a virtual caller, if its execute relay call is the signer we recovered above. Then we pass the message value that was sent and the actual call data. So to verify the permission for a specific payload, we just get the function we get back. So so it's mainly ERC75 function except for these ones. So basically, we get the first 4 bytes of the payload. We compare if it's set data, or if it's set data batch, or if it's execute, or if it's transfer ownership or accept ownership. And and technically, if it's one of these, we then go into one of these verification function. So I don't think it's enough time to go really into this function like in the overall in the like a big detail. But the idea is, so these functions are from the module that inherited above are here in this folder. But yeah, basically the idea of how to verify a permission is to um, so it's to we do it like this require permission. Yeah, it's here. It's in SP6 utils. So we have I try to put things into library so it's usable. It's in it's at the top. Yeah, this one. So like yeah, to verify a permission is like the same as I explained. It's a bitwise end. So we have a permission to check. We have the permission of the address, and if it has the permission, it returns you the same. With the ending, it returns you the exact permission that you wanted to check. So I have an example here in variable. It's somewhere around here. I think it's yeah. So like let's say this is your permissions. You have the bytes 32 value C8, which can be represented in binary as that. So yeah, I think I didn't explain that. I mean, basically each permission it's a bit set into a bit range. So like
Yeah.
the permission change owner is the first bit, the permission add permission is the second bit, transfer value is the third, etc., etc. And yeah, and to check if an address has permission, you take his permission, you do a bitwise AND with the permission to check. If it returns you the actual permission, then it's valid. If it doesn't return you the actual permission, then it's invalid. It doesn't have the permission. Yeah, and I think that's pretty much it really for. I mean, we could go with like more and more into each module, but that would take a lot of time. But yeah.
No, I would love to, but maybe you do a part two or something in the future. Uh, I think perfect timing to stop it here. No, really great overview, and dude, this is super useful. Like this could be like a new key Lego stone that you build your stuff on. So to be honest, I'm surprised that it didn't exist before, which is a really good sign.
Mhm. Yeah,
So
yeah, I think it's great. Yeah, this kind of permission management system. Yeah, yeah, I do like. Yeah, I think it's also. I think the hard part into the key manager, and when it comes to development, it's like the gas. Like you have to fetch the permission from the account. You have to perform the external call, and as we know, external call cost money. So it
yeah,
costs money, it costs gas. So I think it's things like you have to find ways to, like to not consume too much. So you have things like, let's say if like there's a check, like there's something implemented recently where it's if, for instance, like for specific data keys, we compare the new value compared to the old value. So to get the old value, we have to get it to the storage. And depending on it, it's either one permission or the other necessary. So like to
mm,
avoid that, we do things like if a controller has both of these permission already, we we just return early. We return with byte 32 0,
yeah.
meaning no permission needed. So this avoids basically the external call here. So I think yeah, it's the challenge really on the key manager. It's the gas and keeping everything efficient without compromising the security.
No, absolutely. So from a pure software engineering perspective, absolutely makes sense to abstract away your permissions. It's just a lot of gas overhead, right?
Hmm.
Which is
Yeah,
something to consider.
yeah.
But that's always the trade-off we have to make, right? So
Yeah, I think the yeah, it's I mean, especially with I mean, I don't know from your side, but I noticed from when you write smart contract, really, when you comes to the pure logic, it you really soon realize that like it boils down to how you like the way to write efficient code is solidity feels very different than how you write any other type of code. You have to really think of the steps in very different manner. Like you have to end up finding ways to avoid doing certain things. Uh, but yeah, that's really the trade-off. Like you think uh, if it's not necessary to do this to save gas, let's do it. But if you avoid doing certain things, you might be, missing some checks here there. So it's really, yeah, that's really the tricky this case. Yeah,
no, absolutely, absolutely. Yeah, let's hope for layer two, layer three stuff. Maybe in the future, gas will be not as expensive as it is today, hopefully, but it still will cost money, right? So there'll
yeah.
always be gas golfing, gas optimization stuff. No way around that. But yeah, no, awesome, dude. Really, really great presentation.
No, yeah, you're
Um,
welcome. And feel free to to go. I mean, to the talk.luxo.tech. If you go to standards. If you go in the universal profile at SP6, you can see the more all the documentation with everything explained. Um, there are even guides on with JavaScript and how to basically do these things like the granting permissions, getting all the controllers addresses, and executing the relay transaction that I just went through. Uh, yeah, and for if you want to look at the Solidity code, it's the Lukso Network Organization, LSP Smart Contract. You go to Contract, LSP 6 Key Manager, and um, yeah, you will have uh, quite a big chunk of Solidity here.
No, awesome, dude. I will link both the code and the documentation in the description down below. Maybe just out of interest, where is the code base at right now? Is it audited? Is it on mainnet? Where are you guys at?
So right now we actually launched mainnet basically a month ago.
Yeah.
Um, and the code base have been audited quite a lot. We went through, quite a lot of audits. You can even look at them in the audit folder. So yeah, we went through like yes, I mean so far we went through 1, 2, 3, 4, 5, 6, 7, 7 audits. We did formal verification of the contract as well, and yeah, I mean we internally looked at the contract as well, and yeah, we yeah, I think there has been a lot of changes and improvements. But yeah, it has been very audited heavily. Yeah.
Awesome. So ready to use, basically.
Yes, I would say it's early stage of development here, but yeah, it's basically ready to use. Yeah, you can it's very like um, I would say for production maybe early, but maybe
Okay.
it's very early. But yeah, it's ready to experiment with it. Yeah, on testnet. Yeah.
Awesome. Then, John, thank you again for taking the time. If people wanna stay in touch with you, where can I find you?
So you can follow me on Twitter. You can go. My handle is Jean Cavallera. If you look at, you can just Google CJ42, and yeah, and I do also uh, write a lot of articles online on Solidity. Actually, I write an article series called All About Solidity. And yeah, you will you can see my articles there as well. So yeah, it's so if you find things like All About and Solidity topic, that's basically me. Yeah, you can find this article here. And that's yeah, you will recognize it's the same profile picture on my Twitter. So
Awesome.
yeah,
Then I will link to both John's Twitter and blog down in the description below. John, thank you. Thank you guys for tuning in, and see you in the next one. Bye, guys.
see you.